Um, I don't even know who we're recording for, but if the problem is giving us a Bernoulli spiral and it looks something like minus infinity to t, and it's r prime of u, this problem is just a little bit different because we're choosing, instead of a regular a, like most arc length parametrizations, we're taking it to be negative infinity. And we're told that this is just due to some reason of convenience. But the very first thing to do is to figure out what the derivative is. Yeah, so if r of t is e to the t cosine of 4t, e to the t sine of 4t, this is going to turn into, well, we're just taking the derivative, yeah? So that looks like e to the t cosine 4t plus minus e sine of 4t. So I'm just quickly going to crunch this out. The reason I'm actually doing this is because I think that we're going to probably get quite a bit of cancellation. Do you believe me?
Because they're each going to be a derivative of themselves and have themselves
Yeah,
in
and
it,
I also
right?
think that when we square things in order to do this thing, we're probably going to get some sine squared, cosine squared cancellations is going to be my bet. Plus, so this one is probably going to be plus 4 e to the t cosine 4t. Shoot, I should have used u's everywhere, but I think you get the idea. But
Yeah.
yeah, I basically think we're going to e to the u cosine 4u, u. We're basically going to plug this bad boy into this thing right here. And this is just the square root of, the first term squared plus the second term squared. And we're definitely going to get some cancellation because you see where I'm going with this? If you square this entire term, you're going to get like cosine squared for u, which is going to cancel out with a sine squared for u over here. And similarly with these terms. You see what I mean?
Yeah.
Yeah. So it's a little hard to say off the top of my head, but I think this is going to look like e to the 2u cosine squared of 4u. And then over here, it's going to look like e to 2u sine squared of 4u. So what it looks like is a lot of stuff is going to be canceling out. And I'm just going to do this in my head, but I think we're ending up with like e to the 2u plus 16 e to the 2u. Uh, definitely check the math on your own. But then the cross terms are basically going to be what survives. And that's going to be like minus 4 e to the 2u cosine 4u sine 4u. Ooh, but maybe the cross terms end up actually canceling out. You see what I mean? Plus e to the 2u sine 4u. By the way, what am I saying? What I'm saying, does this make sense to you?
The cross term was the cross term.
The cross term. So like when you square this thing, right? You're going to get this term squared plus this term squared, and then you're going to get some cross terms going on, where one of these times one of these, right?
Okay, yeah.
Right, just for foiling it out. So each of the individual squares is going to be really nice because the cosine squared over here is going to have an identity with the sine squared over here. But then the cross terms are actually also really nice because I think this turns into like this term times this term turns into like a minus 8 e to the u sine cosine. But then the term over here is going to be exactly the same, but positive, because you see there's kind of a symmetry here, right? They look super similar. It's just this is a plus sign and that's a minus sign,
Oh,
right? So you get some really pretty cancellation, and what you're left with is really not so bad. I think this just looks like 17 e to the u, something like that. You feel me?
yeah.
And yeah, so once you have that, uh, what is this saying? This is basically saying r prime of u is equal to 17 e to the u, or instead of the 17 just comes from whatever the variable here was, so just fill that out as you please. But okay, then this turns into e to the u times some constant out in front, and well, that's really pretty, isn't it? That just turns into, you can see why they chose negative infinity now, because the integral of e to the u is just e to the u. from t to negative infinity, and this just turns into e to the t. So now we get this really beautiful behavior where s of t is equal to e to the t, right?
It
So
all works out.
s is
Really neat.
exactly, it's so pretty. S is equal to e to the t, so to invert this, t is just equal to ln of s, and this is super cute. And I think at that point you should just be able to plug in the t for the original problem and get what you get. Pretty neat, right?
Yeah, it was actually
Huh?
a lot nicer than I thought it was going to be to me. I must have messed up somewhere along the way.
Right, exactly. I definitely go double check what happens here with the cancellation, because that's what this problem comes down to. The fact that, you know, you're basically really hoping that they contrive this to be really, really pretty. And, you know, you can kind of suspect before doing calculations that there's probably going to be some symmetry because of how similar these things looked, right? The cosine and the sine basically just change position for the x and the y term. And then there's also a sign change. And based on that, hopefully everything works out nice. So, yeah.